Hi everyone, this demo covers the security features we implemented in our Hi-Fi prototype. Security was a core requirement for this project, so we made sure to address it across multiple layers. From how users authenticate to how passwords are stored, to how data moves across the network. I'll walk through 5 areas: authentication and access control, secure password handling, session verification, TLS 1.2 plus transport, and encrypted messaging. Let's get into it. First, authentication. The core principle here is that no part of the app should be reachable without a valid session. When I open the app fresh, I'm immediately presented with the sign in screen. There's no way to navigate around it. This root protection is enforced on every page, not just the home page. Now I'll sign in with the registered account. I don't think I have an account registered, so I'm just gonna. Yeah, cool. Once authenticated, I have full access to the app. Now watch what happens when I log out. I'm immediately redirected back to the sign in screen and the session is cleared. If I hit the back button in the browser, it won't let me go back in. This confirms authentication gating and session based access control are both working correctly. Next, password handling. A common mistake in web apps is storing passwords as plain text. If the database is ever compromised, every user's password is immediately exposed. We avoid this entirely.
When a user registers, their password is hashed using Argon2 ID, a modern memory hard hashing algorithm specifically designed for passwords. We also apply explicit sorting, which means even if two users have the same password, their stored hashes will be completely different. If Argon2 ID is unavailable in the environment, we fall back to SHA-256, so plain text is never stored under any circumstances. The result is that credentials are protected at rest and are not recoverable as plain text even by us. Now, I'll prove the session behavior at the API level, not just the UI. This matters because UI redirects can be faked. What actually counts is whether the backend enforces session state correctly. Step 1, we register and the server issues a session cookie. Step 2, calling the API auth me confirms that the session is active and returns the user object. Step 3, we log out. Step 4, calling the API auth me again now returns null. The server has invalidated the session, not just the client. This confirms that the session management is enforced server side and logout actually terminates the session rather than just clearing a local cookie. For transport security, all communication between the client and server runs over HTTPS with a minimum of TLS 1.2. TLS is what encrypts data in transit. Without it, credentials and session tokens could be intercepted on the network. We enforce this in secure mode using npm rundev secure. I verified this version enforcement with curl. A TLS 1.1 connection attempt is rejected outright and TLS 1.2 succeeds. This means older vulnerable protocol versions are blocked at the server level. Any browser certificate warning locally is a CA trust setup issue, not a problem with the app's TLS configuration. Finally, messaging or implementation using true end-to-end encryption, meaning only the sender and the recipient can ever read a message. The server has access to plaintext content. Each user has a key pair generated on their device. The private key never leaves the client when a message is sent. A fresh encryption key is generated for that message, and the shared secret is derived between the sender and recipient using their keys. This shared secret wraps the message key before anything is transmitted, so the server only ever stores encrypted data. On the recipient side, they used the private key to derive the same shared secret, unwrap the message key, and decrypt the message. Every message uses a unique key and a unique IV, so even a full compromise of one message has no impact on any other.
So the first vulnerability is a DOS attack. So a DOS attack is a type of attack in which the attacker sends repeated requests to the website or server to slow down or even completely crash the website and server. This is a security issue because an attacker could repeatedly send many requests that are expensive to expensive endpoints, such as login or password reset routes. Without rate limiting, the server may waste resources on repeated invalid requests. So that is a main issue. This could make the application slower for users, and in a real world situation or scenario, this could affect availability of the service. So a misconfiguration could be that removing the rate limiter restricts the number of requests that can be sent by a single user, which is an issue of misconfiguration. Um, the some attack steps and outcome could include such as implementing using a script that repeatedly sends requests to our login page. This could slow down the response time to the visit to the site visible through pings to the site. A cause could be that the vulnerability occurs because there is no controlling limiting request frequency per user or per IP address. The server must handle each request instead of rejecting excessive traffic. So, to fix this issue and this vulnerability, we could implement a rate limiter to the site, reducing the number of requests that are able to be sent to our site by a single user. After too many requests are sent by a single user too quickly, it should respond with an error message to the user. Um, and other ways to protect against these attacks include CapCut, which is pretty frequent in most websites nowadays. And monitoring for unusual traffic could also be a way to monitor uh, certain behaviors, unusual behaviors on a website.
Yeah, so how we simulated this attack was we ran a script which sent a large amount of login attempts to our website. And so we removed the rate limiter for the demonstration, which so we could simulate this. And yeah, so it slowed down heavily as the script kept running from like about 500 ms to 2.1k ms. So yeah, as you can see that without a rate limiter or any kind of without rate limiter specifically, our website is very susceptible to to these types of attacks. So like if there's a larger amount of like a larger scale attack, it could completely bring down or slow down our website entirely. So yeah. Writing a weak uh, password storage vulnerability on our website. So in this example, I'm showing what happens when password hashing is removed and the user's password is stored insecurely. So it occurs when passwords are stored in plain text or in a form that is easy for an attacker to read or recover. So for how I'm going to be simulating this attack is a website usually has a hashing algorithm, or we're using Argon 2 for the password hashing. So normally when a user creates an account or logs in, the server should not store the password directly. So and the password should be saved as a hash instead. So for this demonstration, that has been removed and will just be stored in plain text. So password hashing is a one-way process, unlike encryption. It's not meant to be reversed. The actual password in the system would just store the hash password, therefore wouldn't be accessible and isn't reversible. So now I'll show the password, like the insecure password and it being stored. So if I just make an account, and now anyone who has access to the pathway can view any user or account that's stored within our server. So yeah, this just shows the password being insecurely and what the attacker would see if they were to do this attack. Um, so yeah, this issue kind of speaks for itself. It means that all user information is accessible by anyone who can access the website. So which doesn't just impact the service, it also impacts other services as users tend to reuse passwords between sites, so it affects security on other platforms too. So partly why this like password hashing is so secure is mainly because the two so Argon 2, for example, like if you put in the same input, like the same password, it will give you a different output. So it isn't reversible, and you're not able to like reverse engineer like the hashed output to get the original output. So in conclusion, this shows that removing password hashing causes passwords to be stored insecurely. This creates a weak password storage vulnerability because an attacker with access to the storage pathway can directly view other users' passwords. So, yeah.